So now we're going to talk about percentage composition and empirical formula, which is number 6 through 10 in your notes. So number 6 says, find the percentage composition of each element in K2CO3. So what you have to keep in mind is when they say percentage composition, they're talking about percent by mass. So you really need to find the mass of K2CO3. So let's look on our periodic table so we can find the molar mass of that. Potassium, 39.1, carbon, 12.0, and oxygen is 16.0. Since there are 2 potassiums, we'll multiply that times 2. Since there's 3 oxygens, we'll multiply that times 3. We end up with 78.2, 12.0, and 48.0. So if we add that all together, we'll get 138.2. So when we're talking about percentage composition, we're talking about how much of this 138.2 comes from potassium, how much comes from carbon, and how much comes from oxygen. So for the percent potassium, that is 78.2 out of the total 138.2. And since we want that to be a percentage, equals x over 100, or you could say times 100, and x equals 56.58%. For the percent carbon, that is 12.0 divided by 138.2 equals x over 100, and x will equal to 8.68%. And for the percent of oxygen, that's 48.0 divided by 138.2 equals x over 100, and x equals 34.73%. Do notice that I used 48.0 for oxygen and 78.2 for potassium instead of their individual masses, because out of this total 138.2, it wasn't just 16 from oxygen, it was instead 48 from oxygen. And it wasn't just 39.1 for potassium, it was actually 78.2 for potassium. Also notice that if you add these percentages all together, you should get a number that is very close to 100. It doesn't have to be exact, it could be 100.01 or 99.8, but it should be very close to 100. If you get something like 72% total, you know you've done something wrong. So number 7 is more like how you're going to see percentage composition used. How many grams of carbon are contained in 55.0 grams of carbon dioxide? So we need to know the molar mass of carbon dioxide CO2. Based on the periodic table, carbon weighs 12.0, and there are 2 oxygens which each weigh 16.0. So the oxygens add up to 32.0 plus the carbon is 44.0. Okay, so that means that 12.0 out of the total 44.0 is carbon. We want to know if the total is 55 grams, what total is carbon. So we're going to set up a direct proportion. If we're looking at carbon to the total CO2, in 1 mole, carbon weighs 12.0 grams, CO2 weighs 44.0 grams. We want to know how many are there in 55.0 grams, not necessarily in 1 mole. So we'll set up a direct proportion and solve for x. Remember, you're going to cross multiply the numbers that are across from each other, divide by what's left, and we end up with x equals 15.0 grams of carbon. Okay, let's go on to number 8. Number 8 says, calculate the g-atomic mass of a metal that forms an oxide with the empirical formula M2O3. So we're trying to figure out what that M is. It contains 68.4% of the metal by mass. Identify the metal. Okay, so my total is M2O3, but M doesn't actually exist. Oxygen, however, does. So I know that 2 times whatever the mass of M is, plus 3 times the mass of oxygen, which is 16.0, is going to be equal to the total. What I don't know is what is the mass of M and what is the total. But I can still set up a direct proportion kind of like I did before. If it contains 68.4% of the metal, that means if we're looking at metal to M2O3, the metal is 68.4 out of 100. But I can't set that up to anything because I don't know what the metal is. So I don't know what the part metal is, and I don't know what the total is if I were going to try to make a direct proportion. So what do I know? Well, if it's 68.4% of the metal, that means that it is 31.6% oxygen. So instead of setting up a direct proportion with the metal, I'll set up a direct proportion with the oxygen. So that'd be 31.6 out of 100. And even though I don't know what the metal is, I do know what oxygen is. 3 times 16, which is 48. So that's 48.0 of oxygen out of, I still don't know that total. But this time I can find that X is equal to 151.9. I got that by cross multiplying 48 times 100 divided by 31.6. So X is equal to 151.9, which means that my total is equal to 151.9. So now all I need to do is figure out what M is. So I've got 2 times M plus 48 equals 151.9. So that's 2M equals 103.9. And M equals 51.9, which happens to be the same as the molar mass of chromium. So my metal is chromium, and this M2O3 up here really is Cr2O3. Now there's several different ways to work that problem as we did in class, but this one in my head seems to make the most sense. So number 9 is a completely different kind of problem. This time, instead of looking for the percentage composition, we're given the percentage composition and we're looking for the empirical formula. So an empirical formula, kind of like H2O, shows you the simplest ratio of elements in a compound. It's a mole-to-mole ratio or an atom-to-atom ratio, which means in water, for example, there are 2 hydrogens for every 1 oxygen, or 2 moles of hydrogen for every 1 mole of oxygen. It doesn't necessarily mean that the chemical formula actually has 2 hydrogens and 1 oxygen, although it does in water. So let's look for number 9. It says, calculate the empirical formula of a compound with the following percentage composition. We've got carbon with 85.63% and hydrogen with 14.37%. Okay, so we want to know what is the mole-to-mole ratio of carbons to hydrogens. But remember, percentage composition is by mass. So with these percents, we're going to have to try to find a mass. So if we assume that we have a 100-gram sample total, then we can just take this 14.37% and change it to 14.37 grams. And the 85.63% and change it to 85.63 grams. As long as we keep the ratio the same, then that's okay. So, from grams we want moles, because we're trying to find the mole-to-mole ratio. Off the periodic table, carbon weighs 12.0 grams to 1 mole, and hydrogen weighs 1.0 grams to 1 mole. Get out your handy calculator, and that's 14.37 moles of hydrogen, and 7.14 moles of carbon. So the ratio is carbon 7.14 to hydrogen 14.37. But I've never seen a chemical formula like that. And chemical formulas are supposed to have whole numbers. So what we're going to do is divide both of these by the smallest. Dividing them both will keep the ratio the same. And dividing them by the smallest will make the smallest equal to 1. And hopefully the larger one equal to a whole number above 1, which in this case is 2. Which means that the empirical formula is CH2. Okay, so the second part of number 9, we know the empirical formula is CH2, says, if the g-molar mass is 42, find the molecular formula. So remember I said that CH2 doesn't necessarily mean there is only one carbon and 2 hydrogens, just that the ratio is 1 carbon for every 2 hydrogens. So this 42 grams here is what it's supposed to weigh, but CH2 weighs 12.0 plus 2 times 1.0, which is a total of 14. So what am I going to have to do to this 14 to make it equal to 42? And I'll do the same thing to the empirical formula. So I'll say 42.0 divided by 14.0 is equal to 3, which means that if I took 14.0 times 3, I'd get 42. So I'm going to take CH2 times 3 and get C3H6. So the molecular formula is literally how many of the atoms are in a molecule. So even though there's 1 carbon for every 2 hydrogens, the ratio, in this molecule there are actually 3 carbons and 6 hydrogens. The first one is empirical, and the second one is molecular. Alright, only one more problem on this set. Number 10. Determine the empirical formula for the following compound, 70 grams of iron to 30 grams of oxygen. So we're going to set it up, iron to oxygen. We've got 70 grams and 30 grams. So I already have masses, but if I want an empirical formula, that's a mole to mole ratio. So I'm going to take those grams and factor label the moles. Off the periodic table, iron weighs 55.8 grams for every 1 mole, and oxygen weighs 16.0 grams for every 1 mole. Getting out my handy calculator, I get 1.25 moles for iron and 1.875 moles for oxygen. At this step, it's really good to have a lot more significant figures than you need. It will end up making your math come out a lot nicer. Okay, so the ratio is 1.25 to 1.875, but I need that to be a whole number ratio, so I'm going to divide them both by the same number. Dividing them both keeps the ratio the same. Dividing them by the smallest makes the smallest 1. But in this case, the larger one actually ends up being 1.5. So the ratio is, for every 1 iron, there's 1.5 oxygens. But that's not a whole number. So if I keep the ratio the same by multiplying them by the same number, and I can multiply them by a number that makes them both whole numbers, then I'll have an empirical formula that looks better. 1 times 2 is equal to 2. So this is Fe2O3. And there you have empirical formula and percentage composition.